if you look at our calculated confidence intervals for the both rivers, you can see that they are overlapping. For example, 146, if we take 146, they both contain 146, okay? So does it mean that if they are overlapped, we don't see this statistical difference, statistically significant difference, okay? So let's talk about how to compare samples now, how to say if one sample is larger than the other one, or one sample, or we are talking about average in this case. So for example, that VADA is more contaminated than RIBA, or this particular medicine works better than this one. Okay, so how to compare samples? Well, I will use several examples, simulated examples. For example, if we think about the distribution of average values for these samples, these are the curves. The blue curve is for RIBA and the red curve is for VADA. These are the curves that describe it. Okay, and then you can see that there is some overlapping. So it means that it is likely that both rivers have some average chloride content in here, in this value, okay? If we take only 95% cases, there is still some small overlapping. So there is still a chance that both rivers have a value from this interval, okay? So does that mean that there is no difference between the rivers? Or at least maybe we simply don't see it with using these statistics, okay? Let me show you some calculations, okay? So now we have two different samples independently taken from two different populations. In our case, populations are rivers. They may have different sample size, and of course they will have different statistics, average, standard deviation, and so on. Okay. So how to compare the samples? Look, I will use this example. Let's say we have a small lake, 50,000 glasses of water. In this lake, the average chloride content is 145 milligrams per liter, and that's the standard deviation. Okay. In the second lake, we also have 50,000 glasses of water, but the contamination is smaller. We have only 140 milligrams per liter of chloride, but the standard deviation is the same. Okay. Now, what I'm going to do, I will take 10 glasses of water from each lake, calculate average and standard deviation. Then I will repeat it 500 times. So I will end up with 500 average values from each lake. Okay. Let's look at the distribution of these values. So this is this distribution. Okay. So this is VADA. This is VADA. This is RIBA. Let's look at the distributions. This is the real value. This is the population average. And you see, in most of the cases, most of the values vary somehow around this true value. Okay. But I've got some extreme ones, almost 149 and almost 141, right? Even though the true value is 145. Okay. In this case, it's the same. So most of the values are situated around the true, this one. But I've got even 145 and 135. Okay. So there are some extreme values, and this is perfect experiment because I simulated it. So it means that we don't have this non-sampling problems. Okay. So what it means? Does it mean that we still not see a difference? Okay. We have a lot of values, a lot of samples with value, for example, 143, between 142 and 143. You can count. This is about 17. Then we have plus 6, plus 4, plus 7 or 6 here, and so on. So we have some values, around 8%, I think, 8% of the values in VADA, in 8 out of 500, have average values between 142 and 143. And it's about the same here, okay? About the same here. If we compare them together, this is the overlapping cases. These are the overlapping cases, also this one. And this is confidence interval, 95% confidence interval here and here. And you can see that they are also overlapping. Okay, so we have very similar case to what we found in our rivers. Okay, does it mean that statistically we don't see a difference? Well, we know there is a difference. We know that there is a difference in populations. Why we don't see it statistically? How we can calculate something about this difference? Well, the problem is, if you want to compare samples, don't calculate individual confidence intervals. Okay. If you want to compare samples, calculate confidence interval for the difference of average values. That's what we are interested in, right? How big the difference between the rivers is. And if we use normal distribution, it's quite reasonable to use average values to see this difference, right? So what we can do, you remember, if we calculate the individual intervals, the intuition was if we take a lot of different samples and calculate average and then look at the distribution. That's what I did just recently. Then I did the same for the second. I took a lot of samples and look at the distribution. We can do the same for the average. Okay, so the statistic in this case will be a difference of mean values. Okay, the good point is that we already know what to do in this case, and we already know what to do in this case. But if we take just difference of two populations, normally distributed populations, or in this case statistics, the distribution will still be the same. Okay, so we still can use the distribution for the difference. We just need to find out how to calculate standard error for the difference. Okay, let me show you again the example. So here we don't see a difference because the confidence intervals are overlapping. Now I took instead of calculating confidence interval and distribution for separate samples, I took for every of these 500 samples, I took a difference, M1 minus M2. And this is distribution of difference values. The true difference is 5, right? The true difference is 5. So this is the difference. This is the difference, M1, M2 minus M1. M1 minus M2, sorry. M2. And this is the true difference. This is it. Okay, and you can see that most of the time the difference between our samples was about 5. Okay, sometimes I got up to 11, sometimes got up to 1. But look, I never got negative values. So I did it 500 times, but none of the cases I got negative value. What means negative value? It means that it shows me that the second sample is more contaminated than the first in average. Okay, then we will get a negative value. So 500 cases shows all positive values. So we can be sure the first lake is more contaminated than the second lake. How? How big the difference? We don't know. If we calculate 95% confidence interval, this is it. It's somewhere between, let's say, 1 and 9. Okay, so it can be by 1 milligram per liter, by 2, by 3, by 4, by 5, up to 9. We don't know the exact, but we know that at least by 1 milligram per liter, even though the true is 5. Okay, and similarly, like we did it for the one sample case, we can calculate the parameters of this distribution of the difference of means using only one sample. Okay. Yeah. Once again, how to interpret the confidence interval for the difference? Well, the idea is follows. If it crosses 0, some values are negative, some values are positive. Let's say this is 0. Okay, this is 0. Here we have positive difference, and here we have negative difference. This is 0. Okay. Let's say your confidence interval looks like this. So it means that even the smallest possible value for the real difference is positive. So it means that the mu1 is larger than mu2 in this case, right? In this case, like this one, I mean, you always have negative values. So it means that mu1 is smaller than mu2, right? But if you have case something like this, you can be sure. Sometimes you have mu1 smaller than mu2. Sometimes you have mu1 larger than mu2. You can't see this difference between them. Okay, so if you have this case, you assume that they have the same average value. The populations have the same average value. You don't have evidence, you don't have statistical evidence that there is any difference between the populations. Okay, so that's the way to compare populations. You compare average of populations using the samples. Okay, take two samples from different populations, from two different populations. They should be taken independently, and then calculate confidence interval for the difference of average values. If this confidence interval is fully positive, it means that the average for the first population is larger than the average for the second population. If they're fully negative, it's vice versa. If it crosses 0, you don't have an evidence for the difference. Okay, and remember, we always have, in this case, confidence level. So if you calculate it for 95%, that's the 95% of the cases. It's still a possibility that it will not work for the real populations. Okay. Now, how to do that? Very quickly. The idea is the same, but now instead of mu, we have mu1 minus mu2. Therefore, this is our statistic, and this is our standard error. This is our standard error. Okay. Standard error. Okay. So how to calculate standard error? Well, there are different cases. For example, we never know real sigma, right? But for example, we know that they are almost the same. Or we don't know sigma, but they are different. We know that they are different. So there are different cases. I will show you the simplest case, where we assume that the the sigma are the same, and the sample size is the same as well. Okay, so in this case, this is how to calculate the standard error. This is the sample size, and I assume that it's the same for your samples. And you can see that you just take a square of, in fact, you take an average of your variance, and then you divide it to a sample size. Okay.